Hello and welcome everyone to another sessions in the DataHour series. We are thrilled to be here with you this evening for a session full of action-packed learning. I am Kumar Abhinandan, part of data science team at Analytics Vidhya. For those who have joined us for the first time, a brief introduction to DataHour sessions. The DataHour series is a series of webinars conducted by Analytics Vidhya and led by top industry experts. It is a fun way to understand the concepts of data science from leading players in the data tech domain. And as the name suggests, it is 1 hour dedicated to data. We are hopeful that these sessions are going to be great source of enrichments and value adding for our community members. Now on to our session today, which is modern deep learning architecture. Deep learning is a subset of machine learning, which is essentially a neural networks with 3 or more layers. These neural networks attempt to simulate the behavior of human brain, allowing it to learn from the large amount of data. While a neural network with a single layer can still make approximate predictions, additional hidden layers and can help to optimize and refine the accuracy. In this data hour, the speaker will demonstrate the concept of modern deep learning architecture in detail. He'll also do hands-on practical exposures on AlexNet, VGG Net, and so on for your better understanding. I hope you are excited to attend this data hour with us. Before we kick things off and I hand it over to our speaker, a quick recap of the housekeeping items. We are recording the sessions and the recording will be available on our YouTube channel. The link you can find in the chat section. Please use the Q&A sections for asking any questions you might have during the session, and we will do our best to answer them as data hour progresses or towards the end. Lastly, we'll share a feedback poll towards the end. You all are requested to kindly fill up before leaving the session. Now on to our speaker. In this session of Data Hour, we have Sabyasachi Mukhopadhyay with us. Sabyasachi is a research scholar in the Center of Computational Data Science at IIT Kharagpur. He served as a university faculty of Business Analytics and Statistics at School of Management Science, Makaut, which is Government of West Bengal, India. He was also the university course coordinator of BBA and MBA in Business Analytics at Makaut. Sabyasachi was a project scientist at Nanoscope Technologies for a brief period of time. He was the Kolkata lead of Facebook Developer Circle till he is the Google Developer Expert in Machine Learning, Champion Innovator, Cloud, Artificial Intelligence, Machine Learning, Google, and Intel Software Innovator. He is the visiting faculty at Symbiosis Center for Information Technology, SCIT Pune, University of Calcutta, Techno India University, and Webel Fujisoft Vera Center of Excellence. Sabyasachi received MS in Physical Science from IISER Kolkata and was the topper of 2015 batch. Over to you, Sabyasachi. The virtual stage is all yours.
Thank you very much for the generous introduction. I hope I am audible to all of you. I am thankful to Analytics Vidhya for inviting me here on the app of Data Hours. So basically, you see that there may be the participant who have joined, they may have a very strong grip on deep learning, or there may be the participants who are very much new to this particular field, or some of them maybe are looking to get some exposure on this particular session. So before we start, I just want to give you the idea that those who are new to this particular domain, how they can train themselves to be prepared for machine learning and deep learning era. So basically, you see, that definitely you require to know linear algebra at first, basics of the linear algebra along with the eigenvalue, eigenvector calculations, because you will see that, for example, principal component analysis kind of thing, whenever you will explore in machine learning domain, there you will figure out that in those concepts, for understanding those concepts, eigenvalue and eigenvector concept is very, very important. And apart from that, today during our discussion, we'll also see that how we are doing the flattening operation in the final stage of deep learning, which is also an applications of the linear algebra. In the mathematical term, we call it vectorization. And definitely statistics and probability is very much important. Descriptive and inferential statistics is very, very important. Along with that, the probability, conditional probability based theorem is very important, because you see, whenever you go for the Bayesian model or dynamic Bayesian model like Markov model, there will require to have some knowledge on the conditional probability and Bayes theorem. So these are the basic requirement in terms of the mathematical angle. Apart from that, in the programming knowledge perspective, definitely it is always better that if you have the great knowledge in R, because it has an extensive statistical computational support, or at least Python, because if you have the knowledge in Python, Python is a versatile application, but I am talking about the data science angle. So in terms of the Python, you will get a lot of exposures because you see all the data science platforms, basically, all the machine learning frameworks, mostly based on the Python, whether you are talking about Keras, AlexNet, or TensorFlow, PyTorch, these all are the highly Pythonic. So if you know Python, it will be better for you to make a strong grip in this particular domain. So and apart from that, if you see the industry skill requirement as at least JD, job description, what we call, there also you'll figure out that it will give you a lot of exposures. Okay, so after once we can, I believe that these will give you a lot of idea. And definitely one important angle which I want to cover up, those who want to build their career in data science domain, basically one important angle, that is the visualization. Visualization has a very much a good job demand in the market, and Power BI Tableau is also there. Even in India, you can grab these 6-digit salary job per month if you know Tableau. So therefore, you require to know a lot of this kind of the stuffs, which will give you the idea in that particular perspective. And definitely now what we are going to discuss, basically, let me share the screen with all of you, where I am just going to share the screen, and let us start our discussions, explorations on the direction of the deep learning. So just let me know if the screen is visible to all of you. Can you see that?
Yeah, it's fine.
Okay, so, fantastic. So today, basically, we are going to have some hands-on session on deep learning perspective in the Google Colab. Okay, so I believe that those who know already Google Colab, it's fine for them. But those who are new to Google Colab, for them, I'm just giving you how to open the Google Colab and how to utilize it. Okay, so for example, here you can go and just search, just type Google Colab. Okay. And once you open that, you see there one particular link is popping up, that is welcome to Collaboratory. Okay, you just click on it. So there, for example, you can go with the new notebook. Okay, you can click on new notebook there. Once you go there, so once you click on the new notebook, it will appear in front of you. So as you can see, some untitled document will be there. There you can put some name. Okay, for example, we are going to practice the deep learning architecture. So you give some name like deep arc, something like that. Okay, and there you can see plus code and plus text button is available there. So you can click on plus text button once you want to add up some text. Okay, so it will appear like that. You can simply type on it, or otherwise you can click on the plus code button and you can type up the code. And once you are done with it, there is a run cell button section is there in the left hand side, and you can just click on it and it will show you the output. Okay, so this is the how you can execute the entire Colab operation. And let us go back to our discussions. First, we are going to start with the discussions on the AlexNet, how the deep learning scenario has evolved over the period of time. So those are just before going to hands-on execution, I'm just giving you a basic overview on how we came into the deep learning era and how deep learning actually overshadowed the machine learning algorithms over the period of time. So you see that basically machine learning concept actually came up with the mimicking human activity philosophy, with the mimicking human activity in mid of 1940s. And if you see that after that, what happened, a lot of important progress in this particular domain we can see. For example, a lot of interesting methods, including the support vector machine,
Yeah, it's a technical glitch. We are so sorry. Like we'll back with like very softly. Till then, stay tuned. Like we request all of you like to stay tuned. Like our host is will be back very soon. Yeah, like our speaker is back. Like so we will share his
okay,
screen.
I think
No issue. Like it was a technical glitch.
okay, so
Now you can
let
like
me share.
share. Yeah, yeah, yeah.
Okay, just a second, let me share the screen.
Like till then, like who have not filled the like poll, they can fill up the poll. Yeah, sir. You can proceed.
Okay, so sorry for the interruption. I got disconnected because of the poor network, maybe. So anyway, so let us discuss again. And so apart from the binary classification, like I was explaining, you can also have the multi-class classification exposure. Like for example, if you have the normal tissue as well as the grade 1, grade 2, and grade 3 tissues, which are the cancerous. So for example, early pre-diagnosis of cancer in these cases, you can also find out it's a very good problem in the multi-class classification where you are dealing with more than 2 classes. So it can be 3 categories or 4 categories. So this kind of the scenario, we have seen that these machine learning algorithms are really doing good during the 70s, 80s era. But the scenario is that if you check that over the period of time, from 1990s actually, when the internet era came up, we started to deal with a lot of data. I mean, because of the not only the structured data, we started exploring with the unstructured data as well. As you know, that today's era is all about the semi-structured data, because whenever you are posting some images, videos in social media, that is also actually the good example of the semi-structured activity, because your image is the unstructured data, or the video, whatever you are posting, that is the unstructured data. And along with that, the time, for example, your login activity time, logout time, and the overall activity time, that is stored in a structured format. So structured and unstructured holistically, you are generating the semi-structured data. So the abundance of the data has become the pivotal part of our life. And if you see, the digital world is getting double day by day. Now the number of the stars in the universe is equal to the number of the digits in the digital world. So due to that vision, you see the high performance computing is becoming very much important in our life. And although the deep learning mathematical development and the basic development on the deep learning architecture, LeNet, developed by Jan LeCun was done in 1988. But it actually, at that period of time, it actually failed miserably. Today, we will see the parallel comparisons between the LeNet and the AlexNet. Because of a few reasons, in those era, Jan LeCun has not got the support of the NVIDIA, because you see in 1980s, we don't have the GPUs, those high performance GPUs like NVIDIA in that period of time. So that was one of the problem. And the second one is that in machine learning, those who are familiar with, all of you know how the activation function plays an important role on deciding the output. So sigmoid or the tan hyperbolic, if you see the curve of the sigmoid or tan hyperbolic, it is not performance wise scalable. After a certain period of time, performance saturates. You require, whenever you are really looking for something which is performance wise scalable, you require a ramp-like function curve that is present in case of the ReLU. Okay, you can talk about leaky ReLU, parametric ReLU. In every cases, you can see that kind of the presence is there. So during the LeNet development, the activation function has been used as the sigmoid. That is another reason of the failure of that particular model, because in this period of time, support vector machine, decision to random forest, everybody got a better performance than the LeNet. So it was the initial failure of the LeNet model, and the huge buzz around the deep learning actually did not came into the practical picture, which you see in the late 80s. But gradually what happened that once we gradually progressed over the period of time, and we have seen that credit goes to Fei Li, she actually came up with the ImageNet competition. So she realized that when the cloud era started, if you see, the Web 2.0, because earlier we talked about the Web 1.0 when the internet era started, thanks to Tim Berners-Lee and his effort. Then we have seen the rise of the Web 2.0 era, that is the cloud-based, completely cloud-based era. So people realized to store data in cloud and deploy the analytics there. So in this cloud-based era, we have seen that the basic rise of the storing data in cloud and deploy analytics over there. So actually, Fei Li, she actually built the database with 1 lakh features. Why not to store them in cloud and tell the researchers, of the computer vision researchers across the globe, to apply their effective algorithm to classify those tasks. So in 2010, actually, the ImageNet competition came into the picture, and the past structure which got the award, which is the winner of those modern deep learning architecture, that is the AlexNet. Because those whenever we're talking about AlexNet or VGGNet, InceptionNet or ExceptionNet, those which are the modern deep learning architecture, these are the either winner of these ImageNet competitions from 2012 onwards, or they're the runner of those competition. So thanks to the presence of NVIDIA, because GPU, which NVIDIA came up in GPU in 2012, and we also got the support of TPU in 2015. So these two actually gave us a huge support in terms of the deep learning development, and definitely the ReLU-like, ramp-like function, ReLU activation function played a very, very important role in the success of deep learning. So this is the basic background that why this model actually got the huge success, which was not possible during the late 80s and how the LeNet actually felt miserably. So with this background, I'm just going ahead. This particular notebook has been the theoretical part, apart from the coding part, is available. So whatever I have just briefly overview, all those things are present in this particular notebook. You can go through that. Okay, you will figure out all the details there. Okay, so let us gradually move towards the coding portion. So if you see this, so this is the basically in the figure from the left hand side, this is the LeNet structure. So image 28 by 28 image has been taken as the input. And the convolution layer basically do the convolution operation over the input image, and it will figure out all the low level features to high level features from the images. And the average pooling operation, it has been explored there. So average pooling operation, it will basically capture the most prominent features from after the convolution operation. So here you can see there are basically in the LeNet, if you see, there are 2 convolutional layer, okay, followed by 2 average pooling layer, and followed by 3 fully connected layer. So in the fully connected layer is basically connected with basically the output layer. There you do the flattening operation, okay, to extract out the high level features from your images. So basically, as you know, like for example, image is nothing but a matrix like structure, right? So if you have the ABC in the first row, DF in the second row, so like I was mentioning that we can unfold the image in horizontal direction or the vertical direction. So what will happen? Either ABCDF will be in the first row or ABCD will be in the first column. Okay, so either column wise unfolding or the row wise unfolding. So this is the standard practice which is available in the linear algebra. We call them as the vectorization. So this particular trick has been adapted by the deep learning scientists and they named it as the flattening step. Okay, so these are the basic structure which was used during the LeNet model, but as I told you, the activation function was the sigmoid function at that period of time. They have not approached ReLU there. So basic structure of the please look carefully about the basic structure of the AlexNet, which was developed in 2012, because the number of the convolution layer or the max pooling layer or the fully connected layer has been explored there. We will exactly incorporate those things in our coding portion. Okay, so as you can see, so there are basically the three convolutional layer, okay, followed by the three max pooling layer, and after that, finally, there are three more convolutional layer followed by one max pooling layer. The difference is that in earlier case they have used only one average pooling layer. I mean, sorry, only average pooling layer. In our case, we are using the max pooling layer instead of the average pooling layer. And then the final stage, as you can see, the fully connected layer for classifying the 1000 classes. Okay. Although in our case, to get the quick result, we will go with the fashion immunized data instead of the 1000 classes. At the output, you will get the only 10 class. Okay. So with the keeping this architecture in our mind, we are moving ahead for the basic deployment of the overall scenario in terms of the AlexNet. So as you can see that at first stage, what we'll do, we'll install the MXNet. Okay, so in MXNet, basically it is nothing but an open source deep learning platform. And then D2L, which will also the person independent deep learning framework. Then from the MXNet, we'll import NumPy, NP, and NPX. NPX is also will give you the run of all these NumPy stuffs, irrespective of the installation of the packages or not, doesn't matter. Then definitely Gluon will also open source deep learning package that we are importing. Okay, then the basics npx.setup. So we will do all the necessary setups. Okay, then we will basically define the nn.sequential function as net. And then finally, what we'll do, we'll with the 11 by 11 window to capture the object. Okay, so basically there we'll use the stride 4 to reduce the height and width of the object. But remember that our output channel will be much larger than the LeNet in comparisons. So this is the part what we are doing under the net.add. We are defining the first convolutional layer followed by the first max pooling layer. Okay, in the convolutional layer, output will be with the 96 channels with the kernel size 11, stride 4, and the activation function we are keeping the ReLU. Like I told you that we are going to use ReLU there. And the pooling, the pooling window will be 3 by 3 with stride 2. Okay, then followed by that, what we are doing our target will be to make the convolutional window much smaller with the setting the padding 2 there. Okay, for the consistent height and width across the overall output. So basically, our target will be to increase the output channel. So what we are doing there? So basically, nn.con2d. So 256 will be our overall the number of the channel. When the kernel size, we are keeping 5 there. Like I told you, our target will be to reduce down the window. Padding, we are keeping 2. And then activation ReLU. And the max pooling layer, and that we are keeping the pooling size of the 3 by 3 and with the stride 2. Okay, I'm just exploring the steps and then I will show you the execution, how you can do in your case as well. So after doing that, you can check that followed by what we'll do, that there will be 3 successive convolutional layer we are taking. Exactly the architecture which we discussed during the AlexNet, same wise we are basically building here. We are exactly following the architecture of the AlexNet paper, which was done during the ImageNet competition in 2012. Now, our target will be to take the 3 successive convolutional layer, okay, with this little bit smaller convolutional window. So, except the final convolution, what we'll see, the number of the output channel has increased. If you see 384, 384, and the final case, it is 256. The kernel size is, as usual, 3 by 3. padding 1 activation function, we are using ReLU. And after that, what we are taking the max pooling layer, okay, with strike 2. And then after doing that, like I told you, with the help of the flattening step, we are going to incorporate here in the fully connected layer. So basically activation function will be ReLU, but remember that we are going with the dropout 0.5 means 50%. That means that we are trying to avoid the overfitting scenario. Okay, we are not going with the overfitting scenario, because you see the dropout step, what it will happen, it will randomly choose some of the neurons and it will not take it in a final execution purpose. So dropout, we are keeping 50%, and the activation as usual will be there. Okay, and the final outcome, as I told you, that in our case, we are going with the fashion immunized data. So we are not going to classify the 1,000 classes which we which was executed in the AlexNet paper in 2012. We are only reproducing it with the 10 classes. Okay, that's the only difference with the 2012 paper and in our execution purpose. So this particular section, you can see I already have kept one open window for that, for saving our time. So I am just rerunning it. Okay, I'm not anything doing with the final notebook. I am just showing you in the AlexNet demo notebook. So once you click on it, this is the first portion of the code where we have talked about how many numbers of the convolutional layer, overall structures, etc., we have defined. So this particular execution we are doing. So after the successful execution, as you can see, whenever you will run the code in the Colab, after the successful execution, you will see there will be a green tick will appear, and it will give you the time of the running of the code. So here you can see it is 9 seconds, as you can see. You can take some more time, or you can send some lesser amount of the time. So now let me go back there. So this is the basic portion we have executed successfully. And now what we will do, we will move to the next portion. Okay, so there our target will be to construct a single channel data example. Okay, so what we can do, we can access the single channel data example. Now those who are planning to execute the code with me, what I am doing, I'm sharing my GitHub account link with in the chat box. Okay, so what you can do, you will be able to see all those codes, this AlexNet and the VGGNet, which we are going to cover today in a smaller span of time, 1 hour of time. You can easily do that. You can download the code from there. Okay, I will also share the codes with our organizers, so they may also share with you. So this is basically my GitHub repository link. You can go there and you can download it from there, and you can run it by yourself. Okay, the way process I have shown you in the Google Colab. So here you can see these particular 2 codes are already available. You see VGGNet and AlexNet. Okay, these 2 you can download from my GitHub account. Okay, so just a second, let me post it in the comment box section. Okay, so I have shared my GitHub link to the comment box section. Okay, you can access it. Just 2 repository is there. One is with the name of the VGGNet, and the one is AlexNet. You just download it and you run it in the Colab. These all are the executionable code, runnable code. Okay, so nothing to worry about it. And apart from that, I will share all the details with the organizers. So you can, anytime you can contact them and collect it. So nothing to worry about it. Okay, so after once we do that, so now next step will be to construct a single channel data example. Okay, so there basically we will pick up the height and width of the 224. Okay, and it will exactly match with the AlexNet architecture. So basically what we are doing, so for that we are basically creating np.random.uniform distribution with the single channel. So that will be 1, and 224 by 224 will be the height and width corresponding to that. And then simply we are writing net.initialize. After initializing, we are simply running the for loop over it. So layer in net, so x equals to layer of x. Then what we will do, print layer.name output shape x.shape. So that is the way we will print it. So exactly the way we are printing it, you will see just before showing you in the demo portal. Here you see that the way we have defined it exactly, we'll see all the outputs are coming up in the print section. You see layer.name at first. So as you can see, con0, then output shape, we have kept tabs, so give some space, and you see the shape, all the details of the shapes are coming up for the first convolution layer, first pooling layer. Okay, then the second convolutional layer, second pooling layer. Okay, so any Python or Pythonic platform is a zero indexing land, start with zero indexing. So that's the reason the first layer has been marked as first convolution layer as con 0, and the first pooling layer is the pool 0. Okay, so in this way it will give you the output. Okay, then con 1 pool 1, con 2 pool 2. In this way you see all the details. Okay, the way you exactly want to print the output, we have defined it, and it is giving you the output shape of this particular window. Okay, so let me go back to our demo window and show you that this how these codes are running there. Okay, so as you can see, okay, so this part again I am rerunning it. Okay, so you can see it's within twinkle of an eye we are getting the output. So execution time is 0 seconds. So you can see the entire shape the way I have explained it is visible in the screen. Okay, now in the next step, what we have to do the reading of the data set. So all the initial setup is done. Now we are going for the reading of the data set. So like I told you that in the ImageNet paper, they have used for the 1,000 classes, but in our case, we have the shorter span of time. So we are not going with the 1,000 classes, we are going with the 10 classes. So you guys can try it out at your home with the 1,000 classes as the coding structure is given to you. So nothing to worry about it. So here we are going to use with the fashion MNIST data set. So in this fashion MNIST data set, the details of the fashion clothes which are given there, we have to do the 10 class classifications. So basically the lower resolution which we are going to take 28 by 28 pixel, but we have to do the upsample to match with the exact architecture. So that would be upsampling operation to map it to the 224 by 224 class. So if we are doing that, so basically we are keeping it the base size here 128, and you see that the 12.load data fashion MNIST, we are loading the data fashion MNIST. First argument is the base size. Second argument, we are resizing it to 224, upsampling it. So we have kept that. And the result are being stored as the train underscore iterations and the test underscore iterations. Okay, so this is the way we are making this particular operation. So I am showing you this particular operation here in the demo window, where you can incorporate that particular portion. Okay, so here you can run this particular section and you will see the code will run successfully here. So as you can see in the 2 seconds, it took the execution time, and you can see this portion is done. Now in the next section, what we have to do, once we are
So sorry for the inconvenience. I think there is some network glitch. So we'll be back very soon.
Okay, so again, very much sorry, I got disconnected. Just a second, let me share the screen with all of you.
No issue.
I believe that our respected participants will pardon me. It's a network issue, so I am very much sorry. So now you see the learning rate is 0.01 and the number of epochs we are taking is 10. So if you see the overall execution purpose, now over the period of time, the more the number of epoch will go up, you see the training loss is decreasing. Can you see that in this particular the blue color line indicator is showing you the training loss is decreasing, as well as the training accuracy and the test accuracy is increasing. And the final execution, if you are able to see, it is giving us the training accuracy 0.879, that means 87.9%, and test accuracy is even better than that, 88.6%. Okay, so this is how you can check the effectiveness of your model. So this is one of the things which we have discussed for the AlexNet purpose. And as a concluding purpose, we can say that although this particular section, like I told you, that during the executions of the LeNet, the problem was that non-availability of the support of the GPUs, or for example, in the activation function, they have used the sigmoid function. But in our case, we have gone with the ReLU activation functions, and also we are getting the support of the virtual GPU provided by the Google Cloud. So we are getting all kind of the support for the execution purpose. And the last portion of the code, this portion of the code you can run there, it will take 6 to 7 hours of time for the final execution purpose. Okay, so we have only 20 minutes left, so it is no point of running that now. It will take 6 to 7 hours. So I believe those who have downloaded the code from the GitHub, once you can try it out at your home, you will definitely get the outcome which I got here. So it will, like I told you, that it will, for the final step, will take the time to 6 to 7 hours for the execution purpose. Okay, so please try out with reproducing the result, and those who do not have the GitHub account or have some problem in downloading, organizers will share all the materials with all of you, nothing to worry about it. So this is the overall executions of the AlexNet which we have seen. Very popular deep learning architecture, and due to the success of the AlexNet, we last 1 decade, because that was in 2012. Now we are in 2022. So you can see in last over the 1 decade, we are getting the benefit of that outcome, because that actually is, you can see, done the reformation of the entire deep learning era. And because of them, those who are the early stage deep learning researchers, or those who are the very veteran scientists, they got the interest that, okay, so let's explore in the deep learning field and let's see the beauty of the deep learning outcomes. So now let us discuss another important architecture, that is the VGGNet, and why the VGGNet is very, very important, which we'll discuss, because it came into the picture in 2014. So all the architectures which you can see, InceptionNet or ExceptionNet later on, or the ResNet, these all are the either winner of the ImageNet competitions or the runner-up of the ImageNet competition. So they are very vital in terms of the overall development of the deep learning execution. But like I told you, that the VGGNet is why very important, because although it's a shorter span of time, but the way I have discussed the AlexNet background, and then we have done the demonstrations of the AlexNet coding portion, we'll do the same for the VGGNet as well. So in case of the VGGNet, what are the extra benefits which you are getting? Let us discuss one by one. So like I told you, that although basically the AlexNet has given us the very good strong outcome, but the thing is that it has not given us any general template. Okay, how to develop the entire template blockwise approach to get the general development of the architecture. Like somebody XYZ wants to develop some new deep learning architecture, how to execute it. So that benefit you are getting from this VGGNet. The VGGNet, actually, the name stands from the Visual Geometry Group. Visual Geometry Group from the Oxford University. So basically, Gisselman played a very important role in terms of the development of this VGGNet. So on the basis of their name, this particular deep learning network has been renamed as the VGGNet network. Okay, so you will get all the details here. So already we can see in the text section already why the name has been given as VGGNet has been explained there. So it actually helped to develop a general template, blockwise approach, because whenever you will have the blockwise approach, you can generate, you can tweak with that. For example, you can keep 5 convolutional layer and 3 fully connected layers. So it will be VGG8. For example, if you have the 8 convolutional layer, 3 fully connected layer, it will be VGG11. So in this way, you can add on convolutional layer, you can delete some convolutional layer, and you can play it around that which combinations is giving you the optimum result. That you can try out. So that kind of a template was not available during the AlexNet, but during VGGNet, people got some idea that how to build this particular basic model. Once you have this particular building model, then what will happen that you can play it around and you can develop your own model. Okay, so that kind of the benefit you can have with the execution of the VGGNet. And all those other deep learning networks which came into the picture, they actually took the reference of the VGGNet and they got inspired from this awesome work and they basically developed it. Okay, so this VGG block, how we are going to develop the VGG block? So like I told you, that the first part will be to keep the combinations of the convolutional layer along with the max pooling layer. Then the second part will be definitely what we are going to use. This is ReLU as an activation function, which already has shown us by the AlexNet paper that we are going with the ReLU as an activation function. This is going to give us the optimum result in comparison with the other activation function like the sigmoid or the tan hyperbolic. So you can go with that. And then in the definitely the fully connected layers will be there. as at the end. So this is the format which has been followed by very prominent paper written by the Simonian as well as Disherman in 2014. Okay, so we are exactly reproducing the outcome which they got in that particular paper in 2014. Okay, so this is a very, very vital landmark paper, very equally important like what we have observed during the AlexNet, and same thing we are going to observe during the VGGNet. Okay, so let us see. So like the same steps which we will follow here, like the installing of the AlexNet, which is a deep learning open source framework, then followed by the D2L, which is a person independent deep learning framework. And definitely from AlexNet, we are also .gluon, we are also going to import NN neural network, and also from AlexNet we'll import NumPy, NP and NPX person, which will basically the person independent NumPy framework. So now once you do that, our target will be to define, first we will do the setup of the npx.setup, we'll do the initial setup, and then what we'll do, we'll define the VGG block at first, because our target is to generate a basic template, basic block, such that anybody in this world, those who are the initial learner of the deep learning, they can utilize it, they can make their own framework. So that is the beauty of this VGGNet, and that's the reason in the history of the deep learning, VGGNet is a very, very important step, and those who are learning deep learning at the early stage, it is very good to learn VGGNet and try to reproduce those results. Not only that, make your own deep learning, make your own block-based approach. Okay, so that will give you a lot of confidence, and you can make a lot of trial and error and check that which combinations is giving you the optimum result. Okay, so that you can do. Okay, so that is the beauty of the VGGNet model, and that's the novelty of the VGG model. Okay, so there you see what we are doing as usual. Whenever you are defining the function, all of you know that in the function, which portion goes into the argument. As per the basic programming knowledge, you can understand that which things are going to play an important role. So here, number of the convolutional layer along with the number of the channels. These two are playing a very, very important role as the input argument. Then what you will do, you will simply block equals to nn.in sequential. As usual, we are initializing it. Now we are putting this number of the convolutional layer in the for loop. Okay, so for in range number of the convolution, what we'll do, we will keep on adding the basically the nn.con2d. Okay, so nn.con2d under nn.con2d, what we will do, we will take the number of the channel as the first argument, then the kernel size will be the second argument, padding information if required, followed by the activation function information. So number of channel will be the number of channel you want to give there. Then kernel size, we are keeping it 3 by 3 as per their work given in the paper. Then padding 1. Then we are keeping the activation function value. Okay. Now what we will do, we will add up the block. Okay, so now in the block adding, what we'll do, definitely the max pooling layer will go there. Okay, to figure out the most prominent features from it, because convolutional layer, what we'll do in the deep learning, the feature selection is done in the inherent steps. So convolution layer will already has captured the features. Now what will happen? Max pooling layer will pick up the most prominent features from it. So pool size 2 here, stride 2 we are giving there. Then simples the way we define the standard functions in any Python or Pythonic platform, that has been done. Return block BLK. Okay, so that we are going to reproduce here. So for saving the time, already I have opened up the demo window. So I'm just clicking on it, transfer button, to reproduce the result for all of you. So you see it is running there, and once the execution will be done, the one green tick will appear, which we have seen earlier. Okay, so execution is going on there. Okay, so it took 11 seconds to run this particular thing. Okay, so now we are moving to the next step. So once the initial installation and the block definition is being done, now we are moving to the next portion, that is the VGG network, that how this portion is going to give us the overall execution result. So what we'll do, like I told you, the first part is comprising the block. In the block first part, comprising of the convolution and the pooling layer, max pooling layer to be precisely said, and the second part is the fully connected layer. Okay, so this convolutional layer, there will be several VGG blocks which we have defined under the VGG underscore block function in the succession. And then what will happen in the following variable, for example, conv underscore r. So it will consist of the details, one per block, it will be there. Okay, so it will run on the basis of the two values. One will be the convolutional layer, another one is the number of the output channels. Okay, so now At the final stage, what we will figure out, that we will get the fully connected part in the final layer. So basically, if we see this parallel tally, so what you can observe, this VGGNet basically having the 5 convolutional layer. Okay, so 5 convolutional layer, if it is there, and 3 fully connected layer, what will happen in that case? It will be VGG8. If we are taking 8 convolutional layer and 3 fully connected layer, it will form the VGG11. Okay, so there is a parallel tally has been made for your understanding purpose between the AlexNet and the VGGNet. So this VGG block is giving you the basic idea that how the VGG block forms. So number of the convolutional layer followed by the max pooling layer. This is how the VGG block is being formed. You can take 5 convolutional layer like I mentioned, then 3 fully connected layer will form the VGG8. If we have taken the 8 convolutional layer, 3 fully connected layer, it will give you the VGG11. So in this way, okay, 11 convolutional layer, 3 fully connected layer, it will give you VGG14. So in this way, you can make your own general block for it. Okay, so this is the general block structure. VGG block structure is given there already, general template, and followed by 3 fully connected layer as the output. Okay, so this is the general structure of delivering the VGGNet. Okay, so now if we check next step, what we have to do, we have to see that how we are defining the entire structure. Okay, so in our case, we are going to do it with the VGG11 execution. So in the architecture, we have to define the 8 number of the convolutional layer in total. Okay, so that part we are denoting under the conv_arc. Okay, so let us see. So if we are going to execute this particular portion here, so what will happen? Okay, after I'm just reproducing this particular result, and if you see, this is within twinkle of an eye, it has run. Just took 1 second for the entire execution. Okay, so this portion is done. Now again, I am going back to the original notebook. So here, what we have to do, we have to define this particular function conv_arc under the argument. We have to pass the argument under the VGG function. Okay, so it is a simple matter of the for loop which we have to run here. So we are initializing the nn.sequential as net, and then we are defining the convolution part under the for loop. Okay, so under the for loop, you see number of the convolution, okay, layer and number of the channels in conv_arc. Then we are adding up the net.add. Okay, so under the VGG block, 2 arguments we are basically executing there. So number of the convolution layer, number of the channels. Okay, and then the fully connected part, whenever we are defining it, net.add. Okay, so nn.dense layer, you know that we used to define it for the fully connected layer part. Already, all of you are accustomed during the AlexNet, we have done that. So 4096 with number of channel, then activation is the ReLU, and as usual, as I told you, that we are going to use the dropout layer. Here we are keeping the dropout percentage 0.5 means 50%. Okay, so it will basically ignore the randomly some neurons. Okay, from the final execution to avoid the overfitting scenario. Okay, so that it is doing. Okay, then what we'll do, it will just simply as usual, that by rule, the Python, the way you close the for loop, return net, we are doing it. Okay, so this particular part we are executing here. Okay, I am reproducing this particular portion result for you. So you see, this one is being executed here. And you see only 1 second it took to final execution of defining of this particular for loop. Now what we'll go for the single channel data example with a height and width of the 224 to serve the output shape of the each layer. So if we are doing that net.initialize, what we are doing, now we are forming a uniform distribution like we did for the AlexNet case, and we are putting this block under the for loop. Okay, so for BLK net, okay, we are initializing BLK of k as capital X, and then under the we are running the print. Okay, we are executing the print statement, block.name output shape x.shape. So it will give you the exact shape of each of the layer. The way we are printing it, we already have seen during similar kind of execution in AlexNet. And here also you can see the way we'll define it will give you the output. Okay, so you can see all the shape wise sequential 1 output shape, sequential 2, 3, 4, 5, dense 0, dropout 0. Okay, dense 1, dropout 1, dense 2, dropout 2. In this way, you can see all those outputs result has been given there. Okay, so similar kind of stuff where we can execute here as well. Okay, so here also we are doing it, and you can see it is also the reproducible portion. It took only 0 second to give you all the corresponding output. Okay, so once we are done with it, so now we shall move to the next portion. Okay, so as already we have done this defining this entire portion, now our target will be to training part. Okay, so VGG11 is computationally heavy than the AlexNet. Okay, so we have to go in the smaller of the number of the channels. So what we will do, basically, we are keeping the ratio 4 here, okay, and we are doing the final execution, because to make it computationally cheaper, we have kept that particular trick. And now once you do that, so this particular portion, okay, once you run it, so basically it is running. You can see it is also the reproducible one. You can easily practice at your home as well. So now in the next part, what we'll do, we'll make this make the learning rate 0.05. In our earlier case in AlexNet, we have kept the learning rate 0.1. Here we are keeping it 0.05, number of epoch 10, and the batch size 128. Okay, as simple as that. So we are following the other thing as a standard purpose. Already we have seen this particular execution earlier also. So this particular step we are following. And as I told you that this particular execution will take 6 to 7 hours on an average time. So all the notebooks, those who already have downloaded from my GitHub, they can practice it. And apart from that, our organizers will definitely forward that to you. So when you will execute, you will see that this portion is also reproducible. So once you do it, you can see that like the same thing which you observed during the AlexNet, that here also, that with the number of the increasing epoch, you can see the training loss will decrease, and you will get the optimum training and test accuracy. So in our case, if you see, with the same example which you followed in comparison to AlexNet, you are getting the training accuracy 0.935, that means 93.5%, and the test accuracy is 92.7%. In our AlexNet, if you remember, the test training accuracy was 87 point something percent, and the test accuracy was something 88 point something percentage around. But if you see, this VGGNet is giving you the even better result over after executing over the MNIST dataset. So in a general, as you can see, that this particular VGGNet execution is giving you a perfect impact representations of the network definitions. It is quite efficient and elegant, and it is giving a general template for the block-based approach in the deep learning framework architecture designing model. So that's the reason VGGNet plays a very, very important role, and it is, you can say, it's a trend setter in the one of the those people who execute the operations in the modern deep learning architectures. So that due to that reason, I believe that that VGGNet has a very significance in computationally as well as the historic significance in the deep learning development. So these two, the prominent and important modern deep learning architecture, AlexNet as well as the VGGNet, we have discussed so far. All the theoretical support apart from the coding portion in this notebook you will find. So please go through it. If you face any difficulty or doubt, you can email me. I am sharing my email ID in the chat window. Okay, so just a second. So you can contact me over email as well. And also my contact details are available with the organizers as well. You can collect it from them as well. Okay. So just a second, I am writing it there. Okay. And I am resharing my GitHub details. So you can follow me in GitHub, and you can also check it out there. Thank you, John sir, for your kind feedback. Okay, thank you very much. And also, I am sharing I already have shared my GitHub email ID. You can check it out there, and my GitHub repository detail also I'm sharing here, reposting it here again. Okay. Okay. So also I have shared my GitHub account details. So you can see, you can follow me in GitHub, and you can access the codes and all those things. Okay. And also I write some Medium articles whenever I get some time. Okay. So to guide those who are the newcomers in this field, machine learning, deep learning, or data science, you can actually access those things there from there as well. Okay. You can go through those articles if you can follow me in Medium, and you can access those articles as well. Thank you, Benson sir, for your kind feedback. Thank you, Nazir. Thank you, Santanu sir. Thank you very much. Okay. Thank you, Sostik sir, for your kind feedback. Okay, thank you very much. Thank you. And also, I'm sharing my YouTube channel link. There, in few cases, if the organizers give me permissions, I post a few of my talks there. So you can also access those things from there as well. So I have shared all the necessary things from my Medium article link to YouTube channel link. From also, I have shared my GitHub link. So you can contact me anytime. You can also access all those codes and extra whatever you require. And if you have any doubt or any query, you can also email me. I have already shared my email ID. So that would be great. So I believe that I have been able to conclude the inter-session within given time. Now,
yeah. Thank you. Thanks a lot, Sabyasachi. Like, before we proceed to answer your questions.
Thank you, Devadita madam, for your precious feedback. Thank you, Stephen.
I would like to request the attendees to fill up the poll about the feedback, as it helps us to conduct more session. Thanks a lot, Sabyasachi. On behalf of Analytics Vidhya, I would like to thank you for your time and for delivering such a wonderful sessions. I'm sure our audience found it insightful, and hopefully we can conduct more such sessions with you in the future. I hope you guys have filled the feedback poll. If not, I request you to please fill in the poll about feedback, as it helps us to conduct more such sessions. You can find the LinkedIn ID of the speaker in the chat section. And the recording of the sessions will be available in a few days on our YouTube channel. Please find the link in the chat sections of our
Thank you,
YouTube
Shudi ji,
channel.
for your precious feedback. Thank you, Lebi madam, for the precious feedback. Thank you so much.
So we have like few questions from the attendees. Till then, we can if you allow, we can respond to this.
Okay, so you can go with any of them. You can go with AlexNet, you can go with TensorFlow. There is no harm utilizing it. In generally, what happens that whenever you are going for the production level development, TensorFlow is better. For the academic purpose, PyTorch is academicians much more prefer PyTorch. The beauty of the PyTorch is that in the backend they use, although this is a front-end Pythonic platform, in the backend C++ execution is there. So due to that reason, it does the faster execution of the code. So that is the beauty of the PyTorch. But you can go with any of them. Even AlexNet is very effective. It's not only Pythonic. You can there are other programming platform in the front end where AlexNet is also available. So AlexNet has a lot of versatility, and it has all the prominent features which you can get from the TensorFlow and the PyTorch. So you can choose anyone, no problem regarding that. It's up to you. Okay. And if you require the PyTorch or the TensorFlow version of this code which I have executed there, you can email me. I will definitely give you that code, because you see what happens that in generally I give the talk on TensorFlow or the PyTorch. So today I thought that why not to give people some exposure about the AlexNet as well. So that's the reason I have executed all those things in AlexNet. If you require those things which are available for the PyTorch as well as the TensorFlow, I will definitely share those platforms as well. Nothing to worry about it. All the versions, the coding versions, according to those required frameworks, are available there. Okay, so you see that in generally, whenever you go with the, like I told you, that sigmoid and the tan hyperbolic, the problem is that it's not performance-wise scalable. If you see the mathematical curve of the sigmoid or the tan hyperbolic, after certain amount of the scalability, it is saturating somewhere. Okay, but the tan hyperbolic is a ramp-like function. When you are realizing deep learning has been built on the basis of the superhuman philosophy. Okay, so for a human being, whenever you are working for 8 hours, 12 hours, 14 hours, what will happen? Your performance will saturate, you require rest. So our performance, human performance curve is quite analogous with the sigmoid of the tan hyperbolic. But whenever you are going to the ramp-like function, continuous scalable, okay, that's called the superhuman activity. Okay, so that's the reason sigma. If you see the curve of the ReLU, okay, it is continuous scalable. Okay, so ramp-like curve. So what will happen in that case? The ReLU of x, what will get? You will get x for x greater than equals to 0 and less than x less than 0, it will be 0. Okay, also there are leaky ReLU or the parametric ReLU is also there to avoid the vanishing gradient problem. So you can go with ReLU, leaky ReLU, parametric ReLU. You can try out with different activation functions and you can decide. But as I told you, that once you can see the mathematical model and the graphical structure, you yourself will be able to understand that why in deep learning people are preferring ReLU than the sigmoid of the tan hyperbolic. In generally, statistically, if you see all the experts, as according to the expert, sigmoid and the tan hyperbolic will do good once you have the data in order of below 10 to the power 5, but data in order of 10 to the power 5 or more, you will require the basically the activation function, ReLU-like activation function you will require there. You can look, if you are not using Google Colab, you can always you can download. There are, if you check online, there are enough installation guideline for 10 whatever the platform you are using. If you are using TensorFlow or the AlexNet or PyTorch, you will get that. If you face any difficulty regarding installation, you can contact me. No problem, I will guide you. Okay. So what is the main difference GPU and TPU? Look, GPU and TPU will give you the analogous platform. You see that basically GPU has been developed by the NVIDIA. These all are basically to give you the computational support. It's not only about the algorithmic efficacy. Also, along with that, the hardware development is also very important. Let me tell you, all of you know about the cloud computing, right? We are continuously storing data in cloud and deploying analytics there. So what will happen? Continuously storing data in cloud, so congestion will happen. So you require to, offload the cloud. So what you will do? You require, for example, nowadays you may hear about the fog computing or edge computing. So edge computing, what we do? We use the smartphone-based approach. So whenever we are doing the smartphone-based computational approach, you don't have the much processor power there, right? So you go for the algorithmic tree. So for example, if you have an image, okay, so what it will do? If you image is a matrix kind of thing, whenever you go one by one, accessing first row, second row in this way, what will be the order of complexity? It will be order of n square for an n by n image. Now, if you unfold it on the horizontal or the vertical direction, what will happen? So order of complexity will reduce from n square to order of n. Okay, so this kind of the trick people follow for the low processor devices to reduce the overall complexity. Like for example, all of you hear about the CNN, convolutional neural network. Now for a mobile phone based approach, you have the depthwise separable CNN. So these are the approach you can follow. But the thing is that whenever you are dealing with the data in order of 10 to the power 5 or more, so what will happen in that case? You require the support of the hardware development is also important, and that's the reason you require that kind of the high speed processor. So either GPU or TPU will serve the purpose. So TPU was developed by Google in 2015, and GPU was developed by NVIDIA in 2012. That's it. Okay, so that's something. Apart from the mathematical development and algorithm development, the progress of the semiconductor industry is very, very important, and that's the reason it's an historic year. If you say in 2012 or development of GPU or the 2015 TPU. Okay. No problem. You can those models which we have discussed. They all are going to give you the great result for the nonlinear equations, or for example binary, or even for the multi-class classification purpose. Okay. What will happen? Only we have to deal with the two cases. Okay, either basically what will happen from the low level to high level intensity. Basically, the 0 will be denoted by the black one, and the 1 will be for the white one. Okay, so it will be, for example, 8-bit grayscale image, 0 to 255 will be the intensity level. But for example, whenever you are going with the RGB, okay, red, green, and blue, so you have the basically 3 channels are there. So in RGB example, in our case, you can say we have dealt with the 3 channels in our data sets. Okay, and how we are dealing with those 3 channels has been highlighted in the trick. Okay, so you can check out the Python notebook, which has been, you can directly download it from the GitHub, or you can also check out or otherwise, if you have any problem, organizers will definitely email you. You check it out, and if you have any problem, you can email me. Okay, no problem regarding that. So color image processing purpose, GPU, RGB is very much important, and in generally, whenever you are starting on a basically the basic level, if you are starting with the image processing, first you try out with the grayscale image and then go for the RGB. Okay. On a super, you see that nowadays you see our in India, government of India is under the National Supercomputing Mission. Okay, so CDAC is playing important role. CDAC and ISC is heading the overall program. So already all of you know, even in our IIT Kharagpur, we have the 1.3 teraflop Param Shakti, which is a Param Shakti series of supercomputer. So across the globe, you can see there is a rise of supercomputer. For example, in Europe, Atos is the topmost manufacturer of the supercomputer. Okay, so even as far I know, even in India, under the CDAC, when CDAC was looking for the vendor of developing supercomputer, Param Shakti updated version, Atos actually won basically the deal. So you see that in the climate domain and space sciences, there are a lot of uses of the supercomputers nowadays we are figuring out. And definitely, as I told you, that is the common practice. Either 600 teraflop. If you go to either Pune or, for example, IIT BHU, they will figure out the 600 teraflop supercomputers are available. In IIT Kharagpur, 1.3 teraflop computers available, and if you go, IISc is playing a lot of important role in terms of the supercomputer development. Okay, they have their own dedicated center for that. So the rises of the supercomputers are also increasing, and we will see in the upcoming years also. Parallelly, we are looking for the quantum domain, because the present day, like I told you, apart from the coding and the mathematical development, you require the adequate semiconductor development as well. But the present scenario, what is happening, that, like I told you, we can see the exponential growth in the digital world. Every day the digital world is getting double. Okay, nowadays the number of the stars in the universe is equal to the number of the bits in the digital world. So what will happen due to this exponential growth? Whatever the hardware processor we have, by 2035 it will saturate at the present situation. So due to that reason, so we require to move to the quantum domain. And nowadays you guys are hearing about the quantum machine learning, quantum deep learning kind of thing. So apart from the supercomputer, in upcoming days, the quantum computers are also going to play a very, very important role in this machine learning and deep learning domain. Okay, because quantum algorithms works exponentially fast.
And sorry for the inconvenience. Again, like there is a network glitch, something. Although, like, we have concluded the sessions. So I hope you guys have filled the feedback poll. If not, I request you to please fill in the poll about feedback, as it helps us to conduct more sessions. I'm sure like our audience found it insightful, and hopefully we can conduct more sessions with you in the future.
Or query?
Yeah. I think we have wrapped up like with question and answer sessions. Thanks a lot, Savisachi. On behalf of
so much.
Analytics Vidhya, I'd like to thank you for your time and for delivering such a wonderful sessions along with questions and answer from the attendees.
Thank you so much. Thank you so much. I'm very sorry. A few times actually I got disconnected due to the poor network issues. So I'm extremely sorry to the participants. Okay, I hope that this particular session will give you some insight about how to deal with the modern deep learning architectures. I can understand that 1 hour is not good enough for this kind of session, but thanks to Analytics Vidhya for giving me the opportunity on this DataHour platform to share my views as well as to give you some coding demonstration. I am really thankful to them, and I really want to congratulate them for doing such a novel approach to spread the awareness of the data science among the mass level. Those who are the participants, especially the youngsters, those who are the new learner, they will be hugely benefited from Analytics Vidhya as well as this DataHour platform. And that's the reason you see this particular brand name is getting a lot of popularity day by day. So I am really privileged to be the part of it. Thank you very much. Thank you so much. And thanks to the participants for their generous feedback. Thank you so much. I am overwhelmed. Thank you.
Thank you, sir, for your wonderful words.
Opportunity. Thank you so much.
Thank you, sir, for your wonderful words. Now, we'll back with another sessions of DataHour. Please find the link in the chat sections. Till then, bye-bye and keep learning.